In the last class, we have derived the torque speed characteristics of a DC series motor. In a DC series motor, the field winding is connected in series with the armature. And if we neglect armature reaction and saturation, then we can derive a analytical expression for the torque speed characteristics as follows. The generated voltage E equal to K phi f, this is phi f omega, where phi f equal to some K f I a, and therefore, E equal to K K f omega I a. Also, V t equal to E plus I a into R a plus R a c, or V t equal to K K f omega plus R a plus R a c into I a. We can write I a as V t divided by torque is given by K phi f I a equal to K K f I a square. Therefore, torque equal to K K f into V t square divided by K K f omega plus R a plus R a c whole square. Now, this can be written as omega plus R a plus R a c divided by K K f whole square into T e equal to V t divided by square root K K f whole square. This is the analytical expression of the torque speed characteristics of a DC series motor when saturation is neglected. Now, if we plot this, the current speed expression can also be determined in a similar manner. This is the current speed characteristics. Now, if you plot these, both of them the current speed is a rectangular hyperbola with the y axis and the axis at n equal to minus R A plus R A C by k k f as asymptotes. The same thing for the torque speed characteristics. Obviously, at start, that is at n equal to 0, the current and the torque will be determined by the intersection of this curve with the x axis. In normal situation, this current will be almost an order of magnitude larger than the rated current of the machine. So, will be the torque. So, we have seen for DC shunt machine also a similar situation arises. Therefore, it is necessary to limit the starting current even in case of a DC series motor, and that can be done by putting additional resistance in series with the armature. If we put additional series resistance, then this asymptote line goes down, this becomes a minus R A plus R A C plus R divided by k k f, and this characteristics also lowers for different values of R. We can get different characteristics like this. So, it is possible to restrict the starting current at a desirable value by choosing this resistance, external resistance, judiciously. Same thing will happen to torque speed characteristics. However, we see that as the resistance is increased, the current through the machine reduces and so does the torque. Therefore, the machine takes longer time to start. In order to maintain a almost constant starting torque, in that case this resistance should be continuously variable, which is difficult to achieve. So, we use sectionalized resistance as in the case of a DC shunt motor for starting a DC series motor also. like this. These are contactors which can short these sectionalized resistances. So, if we plot the current speed characteristics and the torque speed characteristics with different resistances in series, for different resistances these are with resistance decreasing, total resistance So, suppose we start with the maximum resistance and this will be the starting current, and as the machine speed up, this is the maximum allowable current, let us say I1. As the machine speed up, the current reduces, so does the torque, and at this value let us say we short the first resistance. Since the speed cannot change immediately, it shifts to the next characteristics on a horizontal line and the speed increases further. Then at some point we short the second resistance. The current again jumps and we keep on doing this till we arrive at the natural characteristics of the machine. So, here also we see that we can arrange sectionalized resistance and gradually reduce them in order to get a almost constant starting current and a starting torque. How do we calculate these resistances then? In case of a DC series motor, for that just define certain values. This is the field winding, these are several resistances, so this resistance is RAC, armature resistance is RA, let us say this is Rn minus 1, Rn minus 2, R3, R2, R1, and these are the shorting contactors. Let us say we want to restrict the current between the limits I1 and I2. Let us also define R1 to be Ri plus Ra plus Rac, R2 to be in this manner, R k to be and Rn will be nothing but Ra plus Rac, and Rn minus 1 will be equal to R 1 plus Ra plus Rac. From the diagram we have drawn earlier, we can write I 1 equal to, at start all the resistances are in circuit. So, just when the voltage is applied, the current should be R 1 and the speed at that time is 0. So, I 1 equal to V divided by R 1 . In fact, for any resistance section K, we can write I 1 equal to V divided by K Kf omega K minus 1 plus Rk, where Rk is given by this expression, that is just when the Rk minus 1's resistance has been shorted, the speed was at omega k minus 1. Just when one resistance has been shorted and the new resistance has become Rk, the current is I 1, in which case we can also write I 2, which was the current just before the resistance was shorted, is given by V divided by K Kf. It has to be same because omega cannot change instantaneously. R K minus 1. Therefore, R K plus K Kf omega K minus 1 equal to V divided by I 1 and R K minus 1 plus K Kf omega K minus 1 equal to V divided by I 2. So, R K minus 1 minus R K equal to V divided by I 2 minus V divided by I 1, but R K equal to R A plus R A C plus sigma I equal to K 2 n minus 1 R I, whereas R K minus 1 equal to R A plus R A C plus sigma I equal to K minus 1 to n minus 1 R I. So, R of small r of k minus 1 equal to R of k minus 1 minus R of k equal to V divided by I 2 minus V divided by I 1. So, each of these resistance are equal and of the magnitude V divided by I 2 minus V divided by I 1. So, this is how we can find out the resistances, sectional resistances for starting the DC series motor. Of course, we have to bear in mind that this we have done assuming that the saturation is negligible. If we consider saturation, then there will be some variation in this resistance values. Just as it is important to restrict the current in a DC series motor during starting, The same thing applies for braking also. Now, braking is slightly more involved in case of DC series motor, as we will see. The torque speed characteristics of a DC series motor looks somewhat like this. It does not have a natural no load speed, because at no load the speed tends to become dangerously high. So, as such regenerative braking is not possible. However, we will see how we can achieve regenerative braking by using a chopper later on. However, other two methods of braking, that is dynamic braking and plugging, is possible. Let us see if how we can do dynamic braking of a DC series motor. What happens during motoring mode? The machine is connected to the supply and the armature current flows into the motor. If the machine has to operate in the braking region, it must operate as a generator and current must be fed to the braking resistor. That means the direction of current must reverse. But in a series motor, the problem is if the armature current reverses, then the field flux also reverses. So, the braking will not take place if we simply change over. It is also necessary therefore, while braking, to also reverse the field winding. That is, during braking the connection has to change to the following. The direction of rotation remains same, then with a reverse direction of current, now the current will still flow from S2 to S1 and the flux will still be in the same direction. So, the polarity of the induced EMF will not change. Graphically, we can show it like this. if this is the magnetization characteristics of the DC series motor, then when we want to do regenerative braking and reverse the field winding, then the same magnetization characteristics will be obtained from negative current now. And since the direction of current will change now, the load line equation will be E equal to RA plus RAC minus or in other words, if we keep the armature current direction same, then Vt will still be equal to E plus RA plus RAC into IA, but Vt equal to minus RB IA, hence E equal to minus of RA plus RAC plus RB into IA, which is again a straight line. Which intersects the braking characteristics, the OCC during braking at this point. This will be the value of IA, which shows that IA is negative, that means the current reverses, and this will be the induced voltage. The braking torque will be EB into IAB by omega. It should be noted that during braking, the series motor operates as a self excited series generator. Hence, it will have its self excitation, critical resistance and critical speed. So, as the machine speed goes down, the OCC will also decrease, and at some time it will become tangent to the load line. If the braking resistance remains same, then after some speed the self excited series generator will fail to excite, and hence the braking torque will also reduce drastically. This can be, so there should be a method for varying the braking resistance as the machine slows down. This can be done with the help of a chopper, as we will see. But before that, let us see how we can do plugging. Plugging can be done in a similar manner. Here also we need to reverse the connection of the field winding. But instead of connecting a braking resistance, now this is connected to a voltage of opposite polarity. So, now this will be the magnetization characteristics, and the load line with now the applied voltage is not 0, but a negative value. So, this will be the load line, hence this will be the operating point. We see that for plugging, the value of the braking torque at 0 speed is not 0. So, there is a possibility that the machine will start rotating in the opposite direction. Of course, the current can be very large, hence it will be usually necessary to put additional resistance in series with the armature while resorting to plugging. Even here, as the machine speed decreases, the plugging torque will decrease, and it will be desirable to be able to vary the series resistance. This can be done with the help of a chopper. Let us see. We know that a chopper consists of a two switches, so let us first consider dynamic braking. Here also it will be necessary to let us say this is the normal dynamic braking resistor, and in order to vary it, we connect a switch across it, a controllable switch S, where the S is turned on and turned off at a constant duty cycle or variable duty cycle at a constant frequency. This is the S on, S off. Now, there will be power loss. This is the armature current IA. There will be power loss in RB only when the switch S is off. So, what is the total energy loss? So, this is the time period T. This is the period of T on and T off. So, the power loss over energy loss over one cycle in RB equal to IA square RB into T off. So, average power loss equal to IA square RB into T off by T. If I call this to be delta, the period over which power loss takes place, then this is equal to I A square delta R B. So, this entire arrangement of a fixed resistance and a switch now appears as if we have connected a variable resistance R B, delta R B. Here we have connected a variable resistance delta R B. Since as the machine slows down, the OCC drops, but at the same time the delta can be varied also, so that the braking current and hence the torque remains almost constant. So, with a chopper it is possible to maintain a constant braking current during dynamic braking. More importantly, it is possible to achieve regenerative braking using choppers. So, for that again we will connect the series machine to a chopper. With the field reversed. If this switch is turned on at a duty ratio of delta, we know that the voltage here will be delta V T. Now, since we have reversed the field winding, now for negative current the generated E will be positive. With the chopper, assume positive current direction to be this, we can write delta V T equal to I A into R A plus R A C plus E, or E equal to delta Vt minus Ia Ra plus Rac. So, this is the position delta Vt. We can always get a straight line like this. More importantly, as the so it is possible to choose a value of delta that there is a intersection of this inverse OCC, that is OCC for negative current and the load line. So, you get a operating point, it is at which the series motor will operate, and the braking torque will be Eb Iab by omega. As speed goes down, the OCC will decrease, the delta can be adjusted so that the braking current and hence the braking torque remains more or less constant. This way we can use a chopper to obtain constant torque during either dynamic braking or regenerative braking. Now, let us try to solve a few problems relating to DC series motor to explain to as examples of the concept that we have discussed so far. Let us take a DC series machine whose OCC is given by the following data. Ia equal to 20 ampere, E is 215 volts, 30 ampere, 310 volts, 40 ampere, 80 ampere, 550 volts. Now, Ra plus Rac for this machine equal to 0.5 ohm. This machine is braked by dynamic braking. At 600 rpm, we want that at 600 rpm the braking torque should be equal to 500 Newton meter. What should be the braking resistance? For this, let us first convert the given OCC data in a slightly different format. We know that E equal to k phi omega or k phi equal to E by omega. Also, T E equal to k phi I A, even when we consider saturation. So, the given OCC data, from the given OCC data we can find out K phi and torque for different currents. So, this table can be converted to the following table, that is I A, K phi and T E. So, we do that, and for 20 amperes of I A, K phi becomes 4.1 and T E becomes 82.1. For 30, it is 5.92, 177.63. For 40, $50, and for 80, now if we plot this versus I A, this is K phi and this is T E, this is I A. K phi plot will look somewhat like this and T E plot to some extent like this. So, at 600 so, if I want torque of 500 Newton meter, we can read out 500 Newton meter from here, and the corresponding current I A. So, I A at 500 Newton meter comes out from this diagram, and as well as the K phi from here. .56 amperes and K phi comes to 8.9. Therefore, for 600 rpm, E equal to K phi omega equal to 8.9 into 600 by 60 into 2 pi, this comes to 559.2 volts. But in regenerative braking, E equal to RA plus RAC plus dynamic braking, IA E equal to this, therefore, RA plus RAC plus RB comes to 9.986 ohms, of which RA plus RAC equal to 0.5 ohm, hence RB equal to 9.986 minus 0.5 equal to 9.486 ohm. However, it should be understood that this torque, this resistance RB equal to 9.486 ohm will give a braking torque TB equal to 500 Newton meter at n equal to 600 RPM only. If as the speed goes down, the torque will also go down. Hence, in order to maintain a fixed braking torque, we will need to vary RB, which we have seen can be done using a chopper. Thank you.